Probably Technica also stuff and in English. I guess the Wroclaw University of Science and Technology. Yes. And the title of the talk is Asymptotic Pairs in Topological Actions of Countable and amenable.
So firstly, I would like to thank both Professor Gutman and Professor Przytycki for inviting me here and providing me an opportunity to give a talk on this seminar. And as Professor Gutman said, the title of my talk is Asymptotic Pairs in Topological Actions of Countable amenable Groups. And I would like to present you some new results concerning these subjects, especially to present some theorems which are about connection between topological entropy and existence of asymptotic pairs in topological actions of countable amenable groups with aid of newly invented notion of multiorders. And the part about multiorders will also occupy a huge fraction of this talk. But to introduce this subject, I suppose I would like to start with some historical background. So for classical dynamical systems, and during this presentation, whenever I will talk about classical dynamical systems, I would refer to the systems with actions of the additive group of integers Z, and in case of topological Z actions, I will mean the compact metric space and some homeomorphism T, by which Z acts on this group by the iterates of this homeomorphism. And in measure-theoretic case, I would refer to some measure space and measure automorphism T. So for classical dynamical systems, there is no connection between topological entropy and existence of asymptotic pairs. And in classical pairs, in classical case, asymptotic pairs are defined as follows. A pair of distinct points in a topological dynamical system is called asymptotic if we might say that the orbits of these points approach each other as the time advances. So the following limit of the k iterate of T on the point x and the k iterate of T on the point x prime. As k tends to infinity, this limit is equal to 0. And something is wrong with this pointer because it doesn't work, unfortunately. Yes, but this? No, it doesn't work now. Okay, so I would have to switch slides here, probably.
Sorry for the inconvenience.
Oh, no problem.
Could you please for a moment?
Yeah. So first, in 2002, Blanchrd-Host-Ruette proved the following theorem that if a topological dynamical system has positive entropy, then it admits asymptotic pairs. And later in 2010, now it works. Thank you.
Excuse me, but maybe you should say a word what happens when somebody tries to define asymptotic pairs for both connections. Because that's another.
Well, I will talk about this later. Yes,
okay.
yes. So don't worry. But later in 2010, Downarowicz and Lacroix proved another theorem which states that if a system has entropy 0, then it must be a factor of a system with no asymptotic pairs. And both of these theorems give us a characterization of zero entropy systems exactly as factors of systems with no asymptotic pairs. And there were several attempts known to generalize these theorems for the actions of the wider classes of groups, and of particular interest there are countable amenable groups. But of course, every such attempt will require, or actually would have required the new definitions of asymptotic pairs which would fit this more general setup. And there were two approaches to this problem. One approach was to take a very general definition of asymptotic pairs, which would not refer in any sense to orderability of the group. And this is definition B, which is presented on the slide. And in the sense of this definition, a pair of distinct points is asymptotic if we may say that the orbits of these points approach each other outside of finite sets. So for every positive epsilon, there exists some finite subset of G, such that for every element G outside of this set K, the distance between G of x and G of x prime is smaller than epsilon. And using this definition, Chung and Lee in 2015 proved the theorem stating that if we have a topological dynamical system, but somehow specific, where X is compact abelian group on which a countable polycyclic by finite group acts by continuous group automorphisms, so this is the algebraic action, then if this action is expansive and has positive entropy, then there exists asymptotic pairs in X in sense of definition B. And polycyclic by finite means that if we have the finite sequence of subgroups, then the quotient groups must be either finite or cyclic in this case.
So you have a compact group. In definition B, you assumed countable. So I guess you just replace finite with compact in the definition.
One more time, sorry.
So in the definition you defined the notion for countable.
Yes.
But the theorem, I assume that you.
No, because this space X is a compact abelian group. Yeah. So this is an algebraic action of some countable polycyclic by finite group on a compact abelian group. Yeah, and maybe it's worth pointing out that in 2019, Downarowicz slightly generalized this theorem because he replaced these assumptions about the space X and this group that is polycyclic by finite by a condition that this dynamical system must satisfy a so-called pseudo-orbit trace property. And later, Barbieri, Garcia, and Lee generalized it even further, replacing the condition about the pseudo-orbit trace property with the strong topological Markov property. But it is maybe not as important in case of our talk. But what is important that, as we see, there is, except of the fact that we need a specific space X and a specific group, then also we need an assumption that the action is expansive. And actually, yet in 1999, Lind and Schmidt constructed or provided an example of a topological Z action, which with positive entropy but non-expansive, in which there are no asymptotic pairs which are asymptotic in the sense of definition B. And in 2019, Downarowicz provided another example of expansive Z action of positive entropy in which there are no asymptotic pairs, which shows that this assumption about the expansiveness is necessary, but it is still not sufficient. And it shouldn't be surprising for us, because actually this definition B does not generalize the classical definition. Because if we take for our group the group of integers Z, then for a pair to be asymptotic in sense of definition B, it must be both forward and backward asymptotic. So it must be asymptotic for T and the inverse of T in the same time. So all these theorems regarding the existence of asymptotic pairs using this definition do not generalize the Blanchrd-Host-Ruette theorem. Another approach was to consider only the groups which admit invariant orders. And what it means that on a group there exists a total order, which I will refer to as Pretz from the command in LaTeX. It will be easier for me to talk it. So this symbol defining the order will be denoted by me by Pretz. And this order Pretz is G-invariant if such an equivalence holds that for any elements A and B, A is smaller than B if and only if A times G is smaller than B times G for every element G in the group.
What are examples to know G?
Example. Well, actually, we may take on Z square, also such as spiral, but the order that we take, well, for example, well, we might say lexicographical order on each axis, and then lexicographical orders on another axis. So let's say if the first coordinate is 0, then we have lexicographical order on the second coordinate, and then we move to the second axis. But actually, this order is not very good because it does not produce a Fellner sequence. Actually, it's in this case it's not an order of type Z even, because it has infinite intervals. So I will refer to it later. But for groups which admit invariant orders, Huang, Tzu, and Yi, and Huang, Kaminsky, and Szymański independently showed that if we have a topological dynamical system with an action of a countable infinite orderable amenable group, and if this action has positive entropy, then in X there exist asymptotic pairs with respect to this invariant order, which means that for every positive epsilon there exists some element G0, such that for every element succeeding this G0, the distance between G of X and G of X prime is smaller than
so
epsilon.
this is, I'm rubbish with group theory. So this is supposed to give kind of a notion of plus infinity.
Yes, definitely. But of course, this theorem only is valid for orderable groups, and as we know, not every amenable group is orderable, not every even abelian group is orderable. So,
to make a question to the previous statement. So here we don't require that orderable order will produce a Fellner sequence. What do you require?
no, we do not. Here it is not required.
Okay.
But well, the most important thing about multiorders, which I will refer later, is that multiorders will produce Fellner sequences. So all known generalizations or all known results regarding the existence of asymptotic pairs in positive entropy topological actions either are valid only for orderable groups, or actually do not generalize the classical Blanchrd-Host-Ruette Theorem. And recently invented notion of multiorders, which was introduced in a paper by Professor Downarowicz, Professor Procha, Professor Chang, and me, actually provided us an opportunity to firstly provide new definitions of asymptotic pairs, which would generalize the classical ones, and also to prove generalizations of theorems of Blanchrd-Host-Ruette and Downarowicz Lacroix for actions of all countable amenable groups. So now I would like to move to the part about multi-orders, and of course I will begin with a definition of a multi-order. So first let's take a countable group G, and let's consider a family of all orders on G which are of type Z. So these orders are isomorphic to the natural order on Z. In other words, there is neither minimal nor maximal element in G with respect to this order, and all order intervals must be finite. These are two properties which we require. And this family, of course, can be interpreted as some subset of the space of all relations on G, so it inherits natural topological and Borel structure. And now we can consider the following action of the group G on our set O, namely for every order pret from our set O and every element G, we define the image of the order pret by this element G as an order which satisfies the following equivalence. So A is smaller than B in this new order if and only if A times G is smaller than, oh, there should be B times G, sorry, there is a typo, in the original order.
This is kind of pullback of an order to an order.
Yeah, possibly. And now, if we have some Borel probability measure supported by this, supported maybe is the wrong word because O does not need to be a topological support of this measure, but it means only that this set O is a full measure for this measure nu. So maybe there's a little disambiguation here. And if this measure is invariant under this action of G, then we obtain a measure-theoretic dynamical system O with Borel sigma algebra O nu G, which is called a multi-order. So instead of requiring to exist one specific order which is invariant, we're satisfied with a family of orders which produces a measure-theoretic dynamical system invariant under this action of G. Okay, but so maybe first a very simple example. Later I will present some other examples of multi-orders.
Could you please go back one slide?
Yeah.
Okay, thank you. I was going to ask if it's a probability measure because I have no time to read. Is it somehow obvious that that me always exists?
Well, actually, in this case, we will show that it will exist on for any countable amenable group, but it is maybe not obvious for the first glance that such a measure exists. Well, actually, we'll show that if there exists a multi-order on G, then automatically this group must be amenable. That will be one characterization, but it will be in a moment.
So is the measure final?
Yes, it is probability measure. Yes, it's Borel probability measure. So the very simple example, since the natural order on Z is of course invariant under addition of integers, it is a fixed point for the action of Z given by this formula. Hence, we obtain a trivial multi-order for Z consisting only of one point. Well, as a measure, we of course take the Dirac measure center at this point. So firstly, some might ask whether multi-orders even exist. It was a question, but it turns out that for any countable amenable group, there exists a multi-order. And it can be proved, we provided a proof both, let's say, by construction. So we give a concrete example of a multi-order, but also there is an easier way to prove it using some orbit equivalence theory, which I would refer to later on also.
And I have one more question. I'm sorry, yeah. I think I'm asking too many questions. So, are there examples of non-trivial measures on Z? So, non-trivial multi-orders on Z?
Yes, I will present such an example.
Awesome.
Yes, in a moment.
Okay.
Or maybe in the second part of this talk.
Okay.
Yeah.
I'll wait.
Because I will present a way to construct a multi-order for any countable amenable groups using so-called tiling systems. And I will provide examples of such tiling systems and multi-orders. Actually, we are able to show that for any countable amenable group, there exists a multi-order of measure-theoretic entropy 0. And as I said, the very interesting property of multi-orders is that if we have a multi-order on a countable group, then automatically it has so-called Fellner property. So for almost every order breadth from this multi-order, the intervals of increasing lengths form a Fellner sequence in G, which actually give us a characterization of amenable groups, of course varied for countable groups, because we may say that a countable group is amenable if and only if there exists a multi-order on G. And also, this fact gives us an easy proof that for any countable amenable group there exists a Fellner sequence which, let's say, of exactly the set Fn has in this case length n. Yeah. So Fellner sequence. Where is? So Fellner sequence is a sequence of finite subsets of G, such that for every G in G, name is of So we may say that these sets are sufficiently invariant under the actions of G. This is, of course, the symmetric difference. Yeah. So this is a definition of the Fellner sequence.
Bounded small comparison.
Yes, yes.
Bounded.
Yes. The easiest example for Z, for example, we can take simply the intervals of increasing lengths. Yeah. And this shows us that for any countable amenable groups, there exists a Fellner sequence which each set is increased by one. Yeah, by one element. Because it is not so obvious at first glance. Yeah, that such Fellner sequence exists. Okay, and now I would also like to distinguish some very specific dynamical systems which possess multiorders as their measure-theoretic factors, and such systems are called multiorder dynamical systems. And they are denoted by such a quintuple or sometimes quadruple if we drop the sigma algebra, or sorry, I forgot to exchange the places with mu and sigma in the latter one. So if we have a fixed factor map from a measure-theoretic dynamical system to a multi-order, then we denote a multi-order dynamical system by the original system with added one symbol denoting this factor map. And we have also proved the theorem that every measure-theoretic dynamical system with a free action of a countable amenable group is automatically multi-ordered. So it possesses some multi-order as its factor, and from this theorem we can conclude that for every countable amenable group there exists a multi-order actually. This is one way to obtain the free
action is not free. How does it work?
Well, if the action is not free, then we do not have a guarantee that there exists a multi-order.
Do you have like examples showing both? Probably the positive case of negative.
Well, for negative case, I do not have a specific example. It is similar to the fact that for any free action, in this case, for example, a topological free action, we have a guarantee that there exists a tiling system which is a factor of this action, but for non-free actions we can only get a quasi-tiling system. So it is somehow related to this fact. But I do not have a specific example of a non-free action which do not have a multi-order as its factor. So there is a very interesting property of multi-order dynamical systems. Namely, they are orbit equivalent to a very specific action of Z, which is called, this action is defined by iterates of the so-called successor map. And if we have a multi-order dynamical system, so a system X mu G which factors to some multi-order, then this system is, as I said, orbit equivalent to such a Z action, which is generated by the so-called successor map, defined this way that S acting on X is the same as the transformation by the element G, which corresponds to the direct successor of the unit in order associated with this element X. Yeah, well, because our X mu G factors to a multi-order, then for every X there is some order in O being the image of this X, and this action by S is simply the action by the, you might say, first element in this order. First element is simply, as I said, the direct successor of the unit, because there is also one representation of orders in multi-orders which we call it the anchored bijections. These are the bijections from Z to G, and every multi-order can be represented as a set of anchored bijections. And what it means that it is anchored, it simply means that the element 0 is always mapped to the unit of the group. So the element 1 of breadth is the direct successor of the unit element. So it's the element which succeeds the unit in our order. And moreover, for any k, we have the following formula that the kth iterate of S acting on X is actually the action of, it is a transformation associated with the kth element in the order S. And because multi-order, of course, itself is a multi-order dynamical system, yeah, with its factor being itself, then we can also define a successor map on a multi-order. And then it turns out that this orbit equivalence with the successor map preserves this multi-order factor. So our multi-order dynamical system with actions of G factors to a multi-order, and the orbit equivalent action of Z by the iterates of the successor map also factors to the same multi-order with the action of Z given by the successor map defined on the multi-order. And what is very specific about this orbit equivalence is that it also preserves the conditional entropy with respect to this multi-order factor.
Can you clarify, because a priori it seems that when we define an order on our book, we do not need, which is of Z type, we a priori do not need to say who is zero. Right? We can take the same order and call different element zero.
Yeah, it's not necessary, but it's very convenient to use it in writing some formulas in this.
But the question is, are you now considering another object in some sense? Because you said that you parameterize the orders as elements in 0, 1 to the power of G.
Well, this is one representation, and the other representation is using the anchored bijection. So we can also treat multi-order as some subset of G to Z, yeah, bijection from Z to G. And of course, there is no topological conjugacy between the multi-order treated as a subset of all relations and anchored bijections, but actually in measure-theoretic sense we can exchange both of these representations, but not in topological sense, because in one direction we have a continuous map, but it does not need to be continuous. Actually, the map from 0, 1 to G, from G to G, in this direction it does not need to be continuous. It is continuous in the reverse direction. Yeah, so
it's infinity to 1, it's countable to 1, so there's no.
One more time.
What I'm trying to say is that I know actually on the right hand side you have more information.
Yes.
So many. What would that imply? Yes, that means that you must make a choice.
Yes.
Exactly. So you have one out of countable choices.
Yeah,
so
every shift the.
Exactly.
Yes, we have to. I skip this part because when we are, for example, dealing with such formulas, when we have, for example, k plus j, what is this element of Pretz? Then it actually means that it is jth element in the order k Pretz. So we have to always shift because of this property that this bijection is anchored. Then we have to always move back to 0, let's say.
And so I see the map, but I don't see why it's a measure of isomorphism. I mean, if you take any choice, I don't even see why it would be G-invariant. Yeah, it seems to me not trivial to show that what this map that you this map is not one map. There are many such maps.
That's why we take the one. But if we
No, I'm talking about that. No, you need to make a choice, right?
Yeah.
So let's say you choose something.
Yeah.
Well, but this is not an order because now it's a choice for every thread.
It's a
Yeah.
choice. It's not
Yeah.
about
Yeah.
picking a specific order. It's a choice for every order how to anchor it.
Oh yeah.
And then the question is this map an isomorphism when we consider it the
Well, it is actually. It is. Well, let's say up to a measure. On this up to a measure nu, we have correspondence 1-to-1. Yeah, in this case.
maybe I'm talking to you about it later, right?
Yeah, maybe we'll discuss it later. It is not very important because this is, well, it maybe is important, but in measure-theoretic sense, we have shown that there is, it is not trivial, I agree, because there is a part in this paper, multiorders in amenable group action, which describe it. But as I said, we are not mostly using this because later we will treat with topological dynamical systems, and we cannot use this representation as anchored bijections in this map. Yeah.
Just to check if I understood the notation correctly. So with this quotation, zero breadths would be just unitary
Yes.
of the group. Okay.
Yes. So okay, as I said, this orbit equivalence has nice property that it preserves also the conditional entropy with respect to the multi-order factor. So in this case, well, we have written here because as the theorem is stated, it's stated for the G processes of generated by some finite partitions, but it also means that the entropy of the measure mu with respect to the multi-order factor is equal to the entropy of the measure mu, but under the action of Z by the iterates of the successor map with respect to the same multi-order factor. And it can be proved using some general Rudolph-Weiss theorem regarding the orbit equivalence and the relation between entropy, but also we have presented our own proof of this fact using different argumentation. Okay, so knowing that multi-orders exist on all countable amenable groups, we are able to provide new definition of asymptotic pairs. Actually, the first definition is exactly the same as the one which was used by Huang, Xiu, and Di, and Bułatek, Kamiński, and Szymański. So namely, if we have a topological dynamical system with an action of some countable amenable group, and we have some order of type Z on G, then a pair of distinct points from X is called Fred's asymptotic if the orbits of these points approach each other as we move along these order paths. And this definition is of course valid for all countable groups, but in case of, and the topological actions of these groups, but in case of multi-order dynamical systems, we have another definition of phi-asymptotic pairs. So when we have a multi-order dynamical system, so a measure-theoretic system with some fixed factor from this system to a multi-order, then a pair of distinct points is called phi-asymptotic if both of these elements maps to the same order and they form a Fred's asymptotic pairs with respect to these order Freds. So this is a definition of a phi-asymptotic pairs, and using these definitions, actually firstly the second definition, we prove the first main theorem stating that if we have a topological dynamical system with an action of a countable amenable group G, and if for some Borel probability measure on X, the measure-theoretic dynamical system X mu G is multi-ordered, so it has a multi-order factor, and also if the conditional entropy of this measure mu with respect to this multi-order factor is positive, then there exist phi-asymptotic pairs in X. Well, actually, the set of points which belong to phi-asymptotic pairs has positive measure mu in this case. And I would like to present you the sketch of the proof of this theorem, because this proof is not as long, because actually we are using this orbit equivalence with the specific z action to transfer us from the amenable group actions to the z actions and to use the known results for z actions. So firstly, we are using this formula to obtain that since mu, the conditional entropy of mu with respect to the multi-order is positive, then we also have that the conditional entropy of the mu under the action of the successor map is positive. Hence, we may use the lemma by Guohua-Chang, and this lemma actually states that if a topological dynamical system, we have some G-invariant sub-sigma algebra of the Borel sigma algebra, then firstly, the sigma algebra generates sigma, there exists, maybe not this one, there exists theta such that taking the joining over the all iterations of T, we obtain our Borel sigma algebra. Second, which is maybe not as important because there is also a point about the Pinsker, the conditional Pinsker sigma algebra, conditioned by the sigma algebra. But in our case, it is important that for, this is the same as stated here, that for any pair of points belonging to the same atom of the sigma algebra, I exchanged the we have the same symbols. And any pair of points which belong to the same atom of the sigma algebra theta plus, which is the joining of the, well, we might say that this is the future of the sigma algebra theta under the action of S, then this point must form an asymptotic pairs in this case. And also there is one other point of this lemma, that if the conditional entropy of this is of course up to the measure mu, and if h mu t with respect to theta is positive, theta, no, respect to this guy, then theta plus is a proper sub-sigma algebra of sigma x. And this actually is a generalization or a conditional version of the lemma used by Blanchrd-Host-Ruette in their proof, because they use the similar lemma, but they had here simply entropy, not conditioned by this sigma algebra in this case.
So what is the heart of the idea of this novel, simpler set? Because this, I think, is the heart of the whole.
Yes. So here the idea is that we have some sigma algebra, such that the future of the sigma algebra, separates the points which are not asymptotic.
No, I understand. I'm asking what is the idea behind the proof of this lemma, of this most simple version which was used by Borel and Host and Blanchard?
Well, there is they have taken the, in this case they are using the fact that in this case we have compact metric space, so we can always form a refining sequence of partitions which diameter tends to 0, and there they are taking some joinings of these partitions with this sigma algebra theta and slightly manipulate on them to obtain such a sigma algebra.
Sigma is the object that we need to show exists, no? That's
Theta.
Theta.
Yeah.
So you take so you take joinings of sigma.
No, you take joinings in this case of sigma O, but in this case of this guy to obtain the sigma algebra theta.
Because I guess here, I mean, I think the key question is how do you manufacture? Let's say somebody tells you, okay, I have a positive entropy Z action, and I need to manufacture now at least one positive asymptotic pair, right?
Yes.
So what's the idea? How would I find that?
Well, I will. Okay, so this is the next point. So I thought you were talking about how to obtain this sigma algebra theta.
No, because to me it seems that this is the key.
Yes, this is the key, because since we have such a formula and we know that all pairs which belong to the same atom of this theta plus must be asymptotic, then we use the fact that if entropy is positive, then this theta plus is a proper sub-sigma algebra. Then we obtain that for mu almost every x, this x, in this case, it is a, well, maybe we'll start with the fact that we assume that that we do not have asymptotic pairs. That it means that for mu almost every point, these atoms must be singletons. In this case,
my question. If you agree with me that this is the main step, I'm actually asking what is the main idea behind the main step. In other words, if you have to describe heuristically, how do you find theta?
Oh,
This is my question.
So you are asking actually about theta.
Yes.
Yes. So as I said, you are taking this refining sequence of partitions, and then you are taking some joinings and slightly manipulate, because there are, well, in both Chang's lemma and Blanchrd-Host-Ruette Theorem, this is not simple that we take the joining of theta with some partition from this sequence, but we also have to manipulate this sequence, take some specific elements which are progress. We are taking a specific sequence of numbers kn, a subsequence of n, and we are taking joinings with some iterations of the images of the theta under the iterates of tkn, and then eventually we obtain a sigma algebra theta which is finer than this sigma algebra, and which exactly separates the points, because it is joined with this refining sequence of partitions. It must separate the points which would belong to asymptotic pairs. This is how it's obtained. I do not remember the exact details about it, because there is taken some, because of some technical reasons, there are taken a specific subsequence of numbers, and there are taken such joinings that theta is actually this sigma algebra joined by some tk1 of this refining sequence of partitions. So here is actually, it might be not even different. So maybe this will be tkn. And it is manipulated further to obtain the result. But the key idea is that we are taking the joining with this refining sequence of partitions. Okay, so once we have this sigma algebra by this lemma, then there is only a actually very important step, but maybe quite obvious, that we show that this set of points which belong to asymptotic pairs is in fact measurable with respect to mu, and we do it by showing that this is an analytic set, actually, so it is universally measurable. And then by contradiction, we assume that this set has measure 0, so it would mean that for mu almost every point x, that mu almost every point x does not belong to any asymptotic pair. So in case by lemma 2 we know that any pair of points which belong to the same atom of this theta plus must be asymptotic, it means that for mu almost every atom of this theta plus must be a singleton. So up to a measure mu, theta plus is equal to our Borel sigma algebra in this case. So we obtain contradiction with our point 2. And this is the same idea as it was in the original proof of the theorem of Blanchrd-Host-Ruette. So we are using, simply we are transferring, to prove this, we are transferring from the G action to the Z action. So this proof is rather simple because we are using the known results. Yeah, the only non-trivial thing here, or maybe not non-trivial, but not given previously is this transfer to the Z action. But here is one thing which I need to talk about, because originally lemma by Chang is stated for classical topological actions, so for a compact metric space and for action of Z by iterates of the homeomorphism. And this map S does not need to be continuous in most cases. So, but actually, this lemma by Chang does not require continuity of the map T, because it is using, except of this fact that we are taking this refining sequence of partitions, it is using only some or actually the formulas for the measure-theoretic entropy. So we only need a measurable map, and we need a guarantee that there exists a refining sequence of partitions, and this is guaranteed, for example, if our space is totally bounded. It does not need to be necessarily compact, which is important for the next theorem which I would like to present. And this theorem is a strengthening of the previous one, and it states that if we have a topological dynamical system with an action of a countable amenable group, and it has positive topological entropy, then for actually any multi-order on our group G, and for mu almost every order from this multi-order, there are no asymptotic pairs, so pairs asymptotic with respect to this order. So we may take any multi-order on our group, and with probability 1, we will find asymptotic pairs with respect to any order from this multi-order. And of course, in case if we take our trivial one-element multi-order, then this theorem reduces to the classical Blanchrd-Host-Ruette theorem. Actually, the previous one also reduces, because every measure-theoretic dynamical system factors to this trivial system. Then we obtain that for Z action, actually, the previous theorem is a generalization of Blanchrd-Host-Ruette theorem. And as I maybe mentioned earlier, this theorem actually sheds also some new light on the case of Z actions, because it shows that in positive entropy topological actions, there do not only exist asymptotic pairs which are asymptotic with respect to natural order, but also with respect to many non-standard orders. And I will show an example of such non-standard orders in the second part of this presentation. But let's move to the sketch of the proof of this theorem. So firstly, since we have positive topological entropy, then by variational principle for amenable group actions, there exists a ergodic measure mu on X, for which the measure-theoretic entropy is positive. And then we take such a system, such a product system, that we have our space X, and we take a product with some multi-order. Actually, we may take any multi-order and create such a product system. Since our multi-order is also can be treated as a separable metric space, then this product sigma algebra is also a Borel sigma algebra on a product. And we have a product measure and the product action of G. And since these systems are independent, because we take a product, then the entropy of the measure mu times mu is, with respect to the second coordinates of the multi-order, is the same as the entropy of mu, so it is positive. Hence we may use our theorem 1, which we have proved, and as I didn't say, this is of course a multi-ordered system, yeah, with the factor map being the projection on the second coordinate. So we may use our theorem 1 for this system to obtain that the set of points which belong to phi-asymptotic pairs has positive measure mu times mu. But as you recall, the set A phi was analytic, so its projection on the second coordinate is also analytic, so it is universally measurable in this case. So it is measurable with respect to measure mu, but, well, I didn't say. First, we are dealing with the case where mu is ergodic, because with non-ergodic case we'll deal very quickly. So now we assume that, another thing is that it is easy to show that this projection is G-invariant, because if for some order from a multi-order there exists asymptotic pairs, then we may take the images of this element from this pair by some kth element by the element G to obtain a new asymptotic pair for the order G of pairs. So this set is G-invariant, hence by the ergodicity it must have measure 1, because since the product measure was positive, then the projection must also have positive measure. And it is to be shown, because we have shown that for mu almost every order there exists asymptotic pairs. But as I said, first we are dealing with the ergodic measures, but by the standard ergodic decomposition argument we also obtain the thesis or we also obtain this theorem for any G-invariant measure. So firstly, we proved a theorem, let's say an intermediate step for multi-order dynamical systems, and then using this theorem we have proved, let's say, a nicer version which is stated for any topological action of a countable amenable group. So this is one part of a characterization of zero entropy actions of countable amenable groups. And to get a full characterization, we also need a generalization of Downarowicz-Lacroix theorem. So we need to construct for any zero entropy system an extension which would not have, in this case, phi-asymptotic pairs for actually some multi-order. Because here we have a theorem for any multi-order, then we can create for some specific multi-order. And so far we were using mostly measure-theoretic tools, and of course measure-theoretic tools are not suitable to showing that something does not exist at all. So we need some multi-orders which would have better topological properties, because so far we were only treating multi-orders as measure-theoretic systems. And such multi-orders can be obtained from so-called tiling systems. So the next part of this presentation would be mostly about tiling systems on countable amenable groups, and I'm going to start with a definition of a tiling. So firstly, tiling is simply a partition of a countable group, or tiling on a countable group is a partition of this group into countably many finite sets, which are mutually disjoint, and a tiling is also called proper if this partition has such a property that there exists a finite collection of subsets of G, from which this subset contains the unit, such that every tile of these partitions on every this this set T from this partition is called a tile. And every such a tile is actually some set S from this family shifted by some element C. And this collection of subsets is called the collection of shapes in this case. And because in the latter part I would only use the proper tilings, then I will skip this adjective. So whenever I will talk about tilings, I will always mean proper tilings. And it is necessary to point out that actually tiling does not need to have a unique collection of shapes. There might be many collections of shapes which would produce the same tiling, but we always fix one collection. And also, even if we have one collection of shapes, every tile can be represented in many different ways. It may happen because, for example, we may have let's say on Z square we have such a shape, two shapes which would be identical triangles, but one of them has or maybe to fix this, let's say that unit E is here, and if we place a rectangle somewhere here, then we can have this upper rectangle shifted by some element C1. So let's say this is S1, this is S2, or we can have shifted the second one. Yeah. So there might be many choices. So we always fix one such a representation for every tile, and then we call this set S, which is shifted to obtain this tile T, the shape of the tile T, and the element by which we shifted the center of the tile T. So this is one thing. Okay, and every tiling actually can be treated as a symbolic element. So firstly, we take such an alphabet for which we bijectively assign to every shape from our collection of shapes one symbol, and it is denoted here by S in quotation marks, and we add one additional symbol, say 0, and then we can encode any tiling by the following recipe. So at position G we put element S if this position G is a center of some tile of shape S, or if it is not a center of any tile, then we put here 0. And we can encode any tiling and treat it as a symbolic element. And then if we take a full G shift over this finite alphabet B, and if there is some subshift T of this full shift such that every element of this subshift represents some tiling, then we call this T dynamical tiling. And the simplest example of the dynamical tiling is the closed orbit of some one fixed tiling. Yeah, this is the simplest example. Okay. And if we have a sequence of dynamical tiling, then we can define a system of tilings as actually any topological joining of these dynamical tilings. And of course, the action of this joining is given by the shifts on the each coordinate by the same element, and the elements of this sequence of tilings are of this system of tilings are the sequences of tilings. And this system of tilings is denoted by this sans serif bold T, and the sequences of tilings will be denoted by the calligraphic bold T. Okay, but we want to distinguish some specific systems of tilings which possess some additional properties. So we say that the system of tilings is Fellner if the union of the collections of shapes from all levels arranged in a sequence form a Fellner sequence in the group G. So the shapes from the level from the going with the increasing indices of the levels, then these shapes must be sufficiently invariant. Second property is that the system of tiling is called congruent if any tile is actually a union of subtiles from the previous level, from the level k minus 1.
So not necessarily disjoint union. The union does not need to be disjoint.
Disjoint. It must be disjoint because every tiling is a disjoint union. So it is not possible to have. Well, actually, here we may represent it as tiles, but since we have here the sequence of tilings, then these tiles must belong to this tiling tk minus 1. So they must be disjoint because this is by definition of tiling. And we say that system of tilings is deterministic if we can decompose this, or maybe decompose is wrong word, subdivide every tile into subtiles of lower level, but in a unique way. So roughly speaking, if we look at the tiling at level k, then it determines all the tilings from the lower levels. We exactly know how they look like. Okay. And such a system of tilings, which is Fellner, deterministic, and also minimal as a dynamical system, will be called a tiling system, to distinguish it from the less organized systems of tilings. And there is a theorem by Downarowicz, Kuczek, and Chang stating that for every countable amenable group, there exists a tiling system, and actually there exists a tiling system of entropy 0. And now, once we have a tiling system, we can produce a multi-order basing on this tiling system. And how to do it? Firstly, we start with establishing some ordering of subtiles of every shape. So we know that every shape can be subdivided into subtiles, so we simply order these subtiles, or being precise, we are ordering the centers of these subtiles, yeah? But since in this tiling the centers corresponds to these subtiles, I would refer to it as an ordering of subtiles. And if we establish such an ordering of subtiles at every level, then we obtain so-called ordered tiling system. And since every tile of any tiling can be represented as a translation of some shape S, then of course this ordering on the subtiles of every shape induces also an ordering of subtiles of any tile. Okay, so once we have established the ordering, then we actually obtain here in a local form some order on the elements of the group G. But we need that this order is total order, so all elements are comparable in this case. So we need we have to restrict ourselves to a specific sequence of tilings, and we call them tilings which are in general position. And this means that the sequence of tilings is in general position if the union of the center tiles, so the tiles which contain the unit, grows to the whole group. Yeah, so eventually we cover the whole group. Why we want this? Well, because I will show how to establish the relation between any two elements, A and B, and I will use an example. So let's assume that we have such a tiling system such that on every level the collection of shapes contains two triangles, one oriented upwards and one oriented downwards, and this system is deterministic because every triangle can be subdivided into 4 triangles on the lower level in a unique way. And let's assume that actually here on the picture we have some representation of the sequence of tilings which is in general position. So the center tiles cover the whole group. And let's take any 2 elements A and B, distinct elements. So firstly, we find the smallest common tile, which contains both A and B. And this is why we needed this property that the center tiles grow to the whole group, because we need a guarantee that eventually those 2 elements always will belong to the same subtile, to the same tile. And since this is the smallest such a tile, smallest means that it has it is from the lowest possible level, because it doesn't need to be smallest in the sense of the cardinality. We know that it subdivides into subtiles, and A and B must belong to distinct subtiles. Or maybe I forgot to mention one thing, just for these technical reasons, we always add 0 level to our tiling system, which collection of shape consists only of singletons. So eventually, from level 1, we decompose our tiles into singletons. Yeah, only to obtain this formula that we can compare any 2 elements. And now we look at the ordering of subtiles. And since A belongs to the subtile of the lower number than B, then we say that A is smaller than B in the order generated by this sequence of tilings. Okay, in this manner we obtain a total order, but it does not need to be of type Z. Because it may happen that this element A will always belong to a subtile of the lowest possible number. It will always belong to a subtile of number 1 at any level. So it will mean that it is a minimal element in our order. And eventually we obtain an order of type N. And similarly, if B always belongs, for example, to the subtile of the highest possible number, then we obtain an order of type -N. So again, because in the definition of multi-order we only allow orders of type Z, we need to restrict ourselves to sequences of tilings which produces such orders. And such sequences of tilings are called straight. And we also denote such a set T-str is the set of sequences of tilings which exactly produces orders of type Z. But it turns out that our restrictions is not as strict as it seems to be, because this set of straight elements is big both in measure-theoretic and in topological manner, because it is of full measure for any G-invariant Borel probability measure on our tiling system, and from topological point of view, it is a dense G-delta subset, so it is residual. And now, yes?
I have a question to the operator slide. So in this construction, it's possible that you get some more complicated orders, say like dyadic numbers order or something like that?
Well, I will show you some more complicated orders in a minute, because this is only an example how to establish an order.
As I said here, the interval will always be defined in such construction.
Yes, yes.
So you have them asking if there is an additional problem except the n and -n problem. I think the answer is that there is no additional problem.
Well, actually, it may obtain such an order. Well, here, no. We'll always obtain an order for which we have finite intervals. It is not possible to
Because you have this finite collection of shapes.
Yes, yes, this is
Maybe there is a maximal element or a minimal.
yeah, but there is no problem. For every such sequence of tiles, we obtain an order which has finite intervals. Because eventually they must be contained in the same tile, and all tiles are finite. Yeah?
But you can also have a minimal and a maximal, which is I don't know what type for. Because you can have both problems at the same time.
No, it is not possible.
Infinite. You have infinite number of elements. So, but you, if that would be the case, you would have only finite number of elements.
Yeah, it is not possible to have both minimal and maximal in this case, because we cannot have such a pair of points which would one of them be always in the smallest one and the latter one will be always in the biggest one.
Probably when you say G is countable, you should emphasize that for you countable is not fine.
Yes, I always forget about this. Yes. Oh, so sorry. By countable group, I mean infinite countable. Yeah, because for finite there are many. Well, I would say sometimes problematic things which appear. Yeah.
Yes, I still don't get why you can't have both problems, but I'm gonna skip it.
Because the 2 points will belong to the same type.
Oh wait, because the point blue. Okay, yeah.
Cannot be at the
Yeah.
same time.
Yeah. Now I get it. Thank you.
Okay, so now, since every such sequence of timings which is straight produces a nice order of type Z, then we can define such an assignment that every straight element we assign this order which it generates, and this is a factor from T for any actually Borel probability measure mu on this tiling system. It's a factor, measure-theoretic factor to a multi-order, which is defined as the set of orders generated by these straight elements. And this is well-defined factor because our set of straight elements is a full measure for any Borel probability G-invariant measure. Yeah, and actually this order, this multi-order is very nice because it comes from a dense G delta subset of a nice topological system. It has, it is, I would say, topologically nice enough for us to create a construction with no asymptotic pairs. Okay, but now let's move to some examples of tiling-based multi-orders. So the first, I will finish in, because the time is, because we have 15 minutes more. Okay,
17.
17, okay, so it will be enough. So firstly, let's consider a very easy example. We have as our group Z, and we take such a sequence of timings such that at every level k, we have only one shape, which is an interval of length 2 the power k. Of course, every such tile can be subdivided into 2 tiles of the lower level, into 2 intervals of length 2 to the power k minus 1. And actually, here is the funny thing, because the result, what multi-order we obtain, is only dependent on the way how we order the subtiles. Because from one system of tilings, we can obtain many multi-orders. So let's say that for every k, we will enumerate the subtypes from left to right. So always the left interval will have number 1, and the right interval will have number 2. So eventually we obtain a natural order of type Z in this case. Because we always move from left to right in our order. But let's say that for every odd k, we will enumerate the subtypes from left to right, but for every even k, we will enumerate in the opposite direction, from right to left. And then we obtain such very strange orders. Well, here you have to look, here is the enumeration along the order. So here should be number, actually here is 0, 1, here should be 2, 3, but 2 is actually minus 2 element in our order. So it may be a little confusing, but what it shows that we obtain eventually such an order with infinite jumps. And it is substantially different than the natural order on Z. And our theorem, one of the previous theorems, shows that if we have a positive entropy, then there exist asymptotic pairs with respect to such orders. Maybe not exactly for this one, because we have only with probability 1 such a guarantee, but for orders of this type. Yeah? And here is also a thing that, as you see, the multi-order which we obtain only depends on the way how we order the subtypes in this manner. Okay, so this was an example on Z, but maybe another example on the group Z square. And the construction of this example would resemble the construction of the Hilbert curve, but of course Hilbert curve eventually fills the whole plane, but here we will only stop at the Z elements of Z square. So let T be such a tiling system that at every level k, our collection of shape consists of 4 identical squares of dimension 2 to the power k times 2 to the power k, but we are only labeling them differently. So we are used, for example, such labels, these horse shows oriented in different direction, and we distinguish them. And then each of these shapes can be subdivided into 4 shapes from the lower level according to this recipe. And here also in the numeric matrices we have the ordering of the subtiles in this manner. So let's assume that we have such a sequence of tiling and we look at some tile at level 3. And we have this element here, and we know how it is subdivided into subtiles. So we subdivide it into 4 subtiles, and we know what is the ordering of these subtiles. And now we have a recipe how to subdivide these subtiles to subtiles at level 1. And because we are already at level 1, these subtiles are subdivided into singletons. So once we connect all these points, we obtain something which resembles the Hilbert curve, but it is actually this is the path which we move as we traverse along our order, connected to this, generated by this sequence of tilings. So we may obtain such a multi-order on Z square. Yeah, this graphically very nice example, but it is maybe not very interesting because it not produces any problems, because it has bounded jumps. Yeah, because these multi-orders which has unbounded jumps are very problematic, because we exactly know that they are not closed. They do not form a compact space because of these bounded jumps. If we have bounded jumps, then multi-order is compact. There is nothing problematic about it.
But what is the maximum jump here? Is it 4? Or?
Yes. Yes, in this case it maximum is 4. Okay, so there were some examples of multi-order, of tiling-based multi-orders, and before I will state the generalization of the Downarowicz-Lacroix theorem, I need one more definition, and this is simply a topological version of multi-order dynamical systems. So if we have such a system, topological system, which has a factor being a tiling system via a factor map phi, then we know that this tiling system has a factor being a multi-order, because we have shown it. So we may fix this factor map from x to t, and also fix such a map which assign to every point x an order associated to a tiling to which this element maps. But of course, this order is of type z only for this straight tiling system. So this map is defined only at the pre-image of the straight element. Yeah. Then we obtain so-called topologically multi-ordered dynamical system. And for topologically multi-ordered dynamical systems, we can expand our definition of phi-asymptotic pairs, which are now defined for this map phi. So a pair of distinct points is called phi-asymptotic if, firstly, both of these points belong to the pre-image of the straight element. Secondly, their maps into the same order, not necessarily to the same sequence of tilings, because two sequences of tilings may produce the same order, but they have to map to the same order via map phi, and they are threads asymptotic with respect to this order, which both of them maps. And here is only a remark that since our straight elements are of full measure for any Borel probability G-invariant measure, then for any measure mu on x, we obtain, if on a topologically multi-ordered system, we obtain a measure-theoretic multi-ordered dynamical system, and also any pair which is phi-asymptotic in sense of the previous definition for the measure-theoretic multi-ordered dynamical systems is also phi-asymptotic in sense of this definition. So this definition, as I said, it expands the previous one because it encompasses a larger class of pairs, because we have one universal map for all measures in this case. And now we can state the theorem, which is actually a characterization of zero-entropy systems. So if we have a countable amenable group and we have a topological G action, then the conditions are equivalent, that system has entropy 0, but this is equivalent to the fact that there exists a topological extension of this system and a map phi, which is defined mu almost everywhere for every G-invariant Borel probability measure on Y. And this map is into some multi-order. Well, for every G-invariant measure on mu on Y, this map factors to a multi-order. And there are no phi-asymptotic pairs in Y. So this is actually the same as saying that we have a topologically multi-order extension, and this is point C of our system X, because it may be more understandable with this point C, such that there are no phi-asymptotic pairs in this extension. So for every zero-entropy system, we can construct a topologically multi-order extension with no phi-asymptotic pairs. So we obtained a characterization of zero-entropy systems analogous to the one known for the Z actions in this case. And here is also some bibliography. Here is this paper on which this presentation was based. Unfortunately, it is not yet available in the final form as it will be published, but it is on the archive. And there is also a previous paper about multi-orders and some other papers regarding this topic. So thank you for your attention.
Thank you
Questions?
very much for this very interesting talk. Are there any questions?
I have a silly question, if you can hear me.
Yes, please.
So, I noticed that this paper is going to be published in the Journal of Differential Equations, and I'm wondering what it has to do with differential equations. Also, because now maybe I can submit my papers there, who knows? So that's my question.
Well, mostly why we have chosen Journal of Differential Equations, because we find out that one of the papers regarding this topic by, I suppose it was, where it is? No, not Chung and Lee, but oh, sorry. I believe one of the papers was also published in Journal of Differential Equations, so we have decided that maybe we'll try publishing it also there. There is no particular reason why we didn't think about any connections to differential equations, but of course there are some connections, but possibly people which are dealing with differential equations would be, for them it may be enough to have these results by Chung and Lee and later Mateusz regarding only these actions on compact abelian groups. Yeah, maybe it will be sufficient for that.
My guess is that, asymptotic solutions is a concept that I think is very old. Actually, I think appeared already in the 60s. So in the 60s, you see these people who start working with differential equations, some of them moving into the more abstract theory. So I can certainly see why somebody would think that this concept is very important.
Yeah.
What is the name of the problem that I think Jonathan just mentioned? The problem in differential equations.
No, I'm saying that people were looking in the 60s, for example, when you have a specific system of differential equations and you associate with it a dynamical system, you may be very interested in this concept of asymptotic solutions. So these are two different solutions that in the future are getting closer and closer. It's a very natural concept.
It's related to stable manifold.
Yes, exactly. Exactly.
Okay, that makes sense. Thank you.
I look at this sometimes to the inverse of the unstable manifolds, which make the system chaotic and post-entropy.
Yeah, it is also related because, as we know, positive entropy also implies for classical dynamical systems the existence of the Lie scrambled set. Yes, so the set of points belonging to Lie pair is uncountable. Yeah, so it is a Lie pair. Maybe for people not familiarized, it is if we change the limit in the definition of asymptotic to the well, the lower limit, yeah, lim in, and we say that the lim inf is 0, but the limit does not exist, for example. Yeah? So lim sop is bigger than 0 in this case. So these are points which approach each other, which orbits approach each other only along some sequence, but along this sequence they are still distant. It is also related to this problem.
Can we put a link to your notes?
Yes, of course.
On the webpage?
Yes. It is written in such a manner that it can be placed on the webpage, yeah. Because I would say it is self-contained.
Any other question? If not, let's thank Mateusz again.
Thank you as well.